Hello everyone, welcome to Digital Communication Tutorials. In this video, I'm going to derive an expression for the signal to quantization noise ratio for a mid-thread quantizer. To start with, let the quantizer input x be a sample value of some random variable capital X with mean 0 and variance sigma x square. The quantizer is assumed to be uniform, symmetric and of mid-thread type. Let Xmax denote the absolute value of the overload level of the quantizer and capital delta denote its step size. We may then express the number of representation levels in the quantizer as capital L, which is the number of representation levels, equals to 1 plus 2 into Xmax, which is the absolute value of the overload level of the quantizer, divided by delta, which is the step size. This is one of the way of representing the number of representation levels in a quantizer. Moving on, we know that for a binary code word of n bits, we can have up to 2 to the power of n representation levels. Since the number of representation levels for a mid-thread quantizer are odd, we can write it as capital L equals to 2 to the power of n minus 1. Where L once again represents the number of representation levels of the quantizer and n represents the number of bits in the code word. Let us now compare equation 1 and 2 and solve for delta, that is the step size. So I am taking the RHS of equation 1, writing it here. Then I am taking the RHS of equation 2 and writing it here. So it is 1 plus 2 x max by delta equals to 2 to the power of n minus 1. Let us take this 1 to the RHS. So it will be 2 into x max by delta equals 2 power n minus 2. Let me now take this 2 to the denominator of the RHS. So it will be x max by delta equals 2 power n by 2 minus of 2 by 2. Now I can write 2 power n by 2 as 2 power n minus 1 minus of 2 by 2 anyhow is 1. Now I am going to rearrange this equation for delta to get x max divided by 2 power n minus 1 minus 1. Now to avoid significant overload distortion, we let the amplitude range of the quantizer input, which is x, to extend from minus 4 sigma x to plus 4 sigma x. Please note sigma x represents the standard deviation of the variable x. So when I let the quantizer input to have an amplitude range varying from minus 4 sigma x to plus 4 sigma x, this corresponds to a loading factor of 4. Also, we find that the probability of overload is now set by a value less than or equal to 10 to the power of minus 4. Now, with having these values in mind, let us now rewrite equation 3 by replacing x max by 4 sigma x. That is what is written here. So, delta equals to 4 sigma x divided by 2 to the power of n minus 1 minus 1. Now, we will write an equation for the output signal to noise ratio of the quantizer, which is given as SNR output equals sigma x square divided by sigma q square. Now, previously we have derived sigma q square to be delta square divided by 12. This derivation was discussed in my previous video, which is by the name Quantization Noise and Signal to Noise Ratio. I would like to request you to kindly refer to that video for more information on this derivation. Now coming back, since we have given the value of SNR output as sigma x square divided by delta square divided by 12, let us now replace for delta from equation 4 here. So this is what is written here. That is sigma x square divided by, this is delta, so delta square divided by 12. So now let us take 12 to the numerator, so it will become 12 sigma x square divided by, this is 4 into sigma x square, it is 4 square into sigma x square divided by this complete term square. Now let us simplify further by cancelling sigma x square in the numerator and the denominator. So it will be 12 divided by 4 square is 16, that is what is written here. And here 2 to the power of n minus 1 minus 1 square will come to the numerator now. Upon further simplification, we can write an expression for the SNR output as 3 by 4 into 2 to the power of n minus 1 minus 1 square. Now, If the value of n is large, that is typically if the value of n is greater than 6, then we can simplify equation 6 by excluding this minus 1 term. That is what is being done here. So SNR output is now approximately equal to 3 by 4 into 2 to the power of n minus 1 square. We have excluded this minus 1 term here. So further simplifying, I can write 2 to the power of n minus 1 as 2 to the power of n divided by 2, and then we have the square here. So 3 by 4 multiplied by, this will be 2 to the power of 2n divided by 2 to the power of 2, which is 4. So the final expression for the output signal to noise ratio of a mid-thread quantizer is approximately equal to 3 divided by 16 into 2 to the power of 2n. Quite commonly, we express the SNR in terms of decibels. So in order to express this expression in terms of decibels, let us apply 10 log 10 to both the LHS as well as the RHS. This gives us 10 log 10 of SNR output is approximately equal to 10 log 10 of 3 divided by 16 plus 10 log 10 of 2 to the power of 2n. Now 10 log 10 of 3 by 16 is minus 7.2 plus, now we will take this 2 power 2n term here. So it will be 10 multiplied by 2n, which is 20n, into log 10 of 2, which is 0.3. Upon further simplification, we get it to be 6n. So upon rearranging this equation, I get a final expression for the SNR output in terms of decibels for a mid-thread quantizer as 6n minus 7.2. Please note this is in terms of decibels. By analyzing equation 8, we can state that each bit in the code word of the PCM system contributes to 6 dB to the signal to noise ratio. Right. So that is about the discussion on the signal to quantization noise ratio for a mid-thread quantizer. In my next video, I will be deriving an expression for the output signal to quantization noise ratio for a mid-riser quantizer. If you like this video, kindly press that like button and subscribe to my channel for more videos on digital communication. Thank you for watching. Have a good day.